Okay, sorry for the small delay, and thank you, the organizers, for inviting me here.
So you guys say that from local.
Oh. And I'm sorry to take your chance to introduce.
He's from Toshiba Research Europe, but he's based in Cambridge. It's kind of local. So it's good to hear about his work. Thank you.
Still, laser pointer not working, or is it too weak? Okay. Okay, not. Okay, so now for something completely different, and I see here in the audience Yuri Berkov and Olga Wexler, and if they form one end of a line segment, and Carl Olsen is the other end of a line segment, so my work is somewhere in between the two. And again, so we had Carl Olsen's talk some days ago, or yesterday, on Tuesday, and he introduced nicely what is structure for motion. So just for those people who weren't there, to give a short recap. So structure for motion is essentially you have a large set of images showing, let's say, the same object or the same set of buildings or the same city, whatever. And you, via finding correspondences between those images, so meaning identifying images of identical 3D points or objects, you can compute something like this, which we call, for example, a sparse reconstruction, which gives you an initial idea about the 3D configuration of what you have captured in your pictures. You can, so this is usually called structure for motion or structure from motion or visual SLAM. So depending on which field is your background, you have slightly different terminology, but at the end it's the same. You can go one step further. So given this kind of information, so this sparse point cloud, plus what you also get as a byproduct, and you're usually most interested in this, are the position of the camera, so where the pictures were taken. If you have the two things together, then you can create what we call a dense 3D reconstruction using this information, and this can be used. Yes, this is Vienna, this is the Graben. So this was like 10 plus years ago, so these days you can do much better and much nicer and much easier to recognize, but just to give you an idea what you can do, and these models can be used for, I mean, basically entertainment, so somehow visualizing or to reconstruct objects, delicate objects, to be on this virtual display in museums, so for cultural heritage preservation. It can be used, one of early goals was for flooding simulations, for example, etc., etc. And my talk will be again two very different topics, and one is when I call it when lifting helps, so making a function or optimization problem look more complicated and you get better solutions. And the second part will be one interesting instance, especially in structural motion, where exactly the opposite is the case. And the first is, so that's where I'm closer to Yuri and Olga, random field inference. Luckily, I start with being only on discrete domains and with discrete label sets. So random field inference, what is it? So imagine you see an image as, let's say, intensity values or color values on a two-dimensional lattice, and you have, for example, given a noisy image, and you want to have a clean image back. What you do is you formulate as a labeling problem, so where the input image, the noise image is given, and you have like what we call a data term, that your unknown value you're interested in should be somehow close to this observed value. Plus what we call the second term, the Paris term, is a regularizer that, for example, in your solution, labeled pixels should roughly correspond to some natural image statistics. And this is usually a tough problem because of non-convexity of the underlying problem. Another example would be, so here we have like intensity values that are your unknowns. It could be, for example, semantic categories. So this is another important application these days, and this goes very close to Olga's and Yuri's presentations. So what people do in order to make this problem more tractable in the general configuration is they lift it into some higher dimensional space, and usually for efficiency reasons they consider them some corresponding LP relaxations. So on the bottom you see the LP relaxation, and so this unknown quantity x is basically a vector for each pixel in the image or for each node in the graph in the more general configuration. That tells you it should be 1 for this vector should be all zeros, but a 1 at the position that tells you which unknown label is the right one to pick at node S or pixel S. And so this is a very successful model used in machine learning and computer vision a lot. And one of the questions that arises is when is this relaxation time? So it is known that the relaxation, and because the general problem, the multi-label label assignment problem is generally NP hard, so very difficult. This relaxation can be solved in theory in polynomial time. In practice, because of the very special structure, you don't use generic solvers, but you use very fast approximate solvers that give you very good solution in a very short amount of time. But still the question is when is this relaxation type, because it also tells you what are kind of difficult problems that this LP relaxation is not going to solve well, and what are kind of problems that the relaxation is going to address very well. And there's a number of results. So there's obviously no characterization of when you can solve it well in the in the general multi-level case, but there's a set of sufficient conditions that exist in literature. One I'm going to mention more in detail on the next slide, or next set of slides, is convex pairwise potential. So meaning you penalize differences in the assigned labels such that this function, how to penalize the difference, is a convex function. So this is a quite well-known result in the literature, and this is usually attributed to Ishikawa. And another one, the more general one, is so submodularity extension to multiple labels, and there exists an even more general version that's called permuted submodularity. But I'm not going to talk much about this. So what does it mean? Convex pairwise potential. So you have two labels, you look at the difference, and then how you penalize label differences should be a convex function. And because we here work with discrete label sets, this means we can restrict ourselves to piecewise linear convex functions, because we don't need the extra power of general convex function. And it also means that we can rewrite, what we are going to use on the next slide, is to rewrite this piecewise linear convex function as a sum of basically a linear term that's at the end, plus a sum of some kind of hinge loss-like functions, so which is a truncated L1 styler functions. So meaning if the argument is positive, you keep it, so it's linear in that sense on the positive range, but if the argument is negative, you clamp it to 0. And you can decompose every piecewise linear convex functions in that way. And if you realize this, you have I believe, very intuitive graph code construction that brings me back to Yuri's presentation, I guess, a lot. How to see, first how to solve it, and how to see that the convex relaxation is tight. So what you see here on the left, usually when you read these graph code papers with multiple labels, you very often see these kind of pictures where you have two adjacent pixels. These are all represented by columns, and the height where you put the cut in the column is corresponding to which label you assign in your solution at this pixel. And so you put two columns to illustrate what are the pairwise interactions that are used. So on the left you see kind of this, what you call sort of L1 interaction. So for a particular cut that is indicated in the graph, that's indicated by the red curve, you see on the left pixel, or the label change from left to the right pixel is 2, because the cut on the right pixel is 2 levels higher. So, and you pay, in this case, the cost 2 times alpha. You would not pay anything if the cut would be reversed, so you would have the higher labor on the left and the lower labor chosen on the right. And the other aspect that comes in is, in order so the left one would be able to model what we call like L1 type or total variation type interactions. The right model allows you to use more general convex function, so you just shift basically these errors to higher labels. So it means if you have on the right hand side, again, you have a labor difference of 2, but because you have these slanted edges in your graph, you only cut one of these edges, even if your labor difference is 2, so you pay the price alpha, another alpha in this case. So this construction allows you to reformulate or actually solve this problem of random fields with discrete labels, but these pairwise convex potentials using a graph cut construction. So kind of a corollary, you can write down what is the LP relaxation in this case. People familiar with this will recognize kind of the unit terms and some pairwise interactions, and via this construction you clearly read off that you obtain a tight relaxation, so you always get an integral solution that tells you which labor exactly to choose for each of the pixels. So this was discrete domains, so viewing the image as a two-dimensional lattice and a discrete labor space. So what about the kind of the other extreme? You have continuous, you view the image or as function over a continuous domain and taking continuous values. And in one of the, I guess now relatively known literature or works is by Alberti from 2003, who analyzed the Mumford-Shah function and proposed a convex relaxation into continuum, so indicating how this is working. I'm not too familiar with it. I only get rough ideas, and it's not that important for you. But basically, you represent everything in terms of their, let's say, what's called sub-level functions. So you look at the epigraph of your solution, and you model kind of how are the interactions in this epigraph formulation. So the convex relaxation looks like above, and what Fock and Chambord basically have shown in their paper is first, if the pairwise interaction is convex, then the continuous or the convex relaxation in a continuum is exact. So you get back true optimal answers for your original problem, so you don't pay anything for looking at the convex relaxation. And they proposed at the end, I would say, kind of a straightforward discretization scheme and optimization method to actually solve it for finite dimensional problems. So far so good. The only one thing that turned out is if you look at the discretized formulation, so working on image lattices and some also your label space is discretized, you end up that in practice, although the theory tells you in the continuum you should get exact answers, so meaning you should have a proper sub-level function as result, so that jumps from, let's say, 0 to 1 or 1 to 0 at exactly one point. Because of the, let's say, discretization artifacts, you're not observing that. So one of the things, and you're not observing that even if everything is a convex problem. So for problems that could be kind of trivially solved in the first place. So one thing I'm interested in, was always interested in large label spaces. So if you either have a very large number of labels or even then continuous labels, but because of certain reasons you want to keep the discrete nature of the underlying domain. So in the community, basically there are kind of three cases. So if you use discrete labels or continuous labels, but you quantize this continuous label space, then you are in the domain again on using discrete labels and discrete domains. So that's relatively well understood. You have the second case, so you keep your continuous labels, but you are lucky enough that everything looks like convex. Then it's also very easy to solve. And one setting I'm addressing on the next slide is what if your involved functions are piecewise convex. So you keep the continuous label space, but you add a bit of structure on a function that is less trivial than using convex function in the first place. What I'm going to use is some little fact that at least seems not to be known in the computer vision community before. So it is a generalization of the fact that you can rewrite the minimum of finite number of values by optimizing over the simplex. And so you can generalize this fact to if you have a set of convex functions and you want simultaneously finding out which of the functions takes the minimum and where is the minimum in the continuous space, you can rewrite it like this, as shown on the right hand side, which makes it possible to just pull out explicitly variables, and it allows you to do constructions like dual decomposition in order to extend this on larger scale programs. What shows up here is the perspective of a convex function, which is also not too well known in the computer vision literature, but it starts to emerge quite often in these kind of programs. And this perspective function in certain situations can be interpreted as a convex relaxation of an if expression. So like, for example, in the bottom you have an if x equals 1, then you return f1 of that, otherwise you return f0 of that. And kind of a convex relaxation of this expression is also involving this perspective and a similar construction as above. Okay, now back to the setting, so discrete domain, but still retaining continuous labels, but you have these piecewise convex functions. You can rewrite a convex relaxation like this. I'm not going to explain much, but it reduces to well-known this well-known P relaxation if you make these functions, involved functions, piecewise constant. So then basically this extra set of variables y disappears and you're back to the LP relaxation. Otherwise it's a kind of strict generalization. And why is this potentially interesting is, so one of the programs or sub-programs in stereo, or in let's say 3D computer vision, is solving the stereo correspondence problem, where I've given, let's say, 2 images, and you want to densely, so for each pixel, find a corresponding point in the other image, which indirectly translates to obtaining what we call a depth map. So you know the depth, so the 3D distance of the pictured object for each pixel. So that is a very important problem to go, for example, from this sparse point cloud towards the dense point cloud. And so you can think of also these displacements or these depth values. This can be a large number to test for. So compressing or having a more compact formulation to solve this problem. So this was one of the motivating examples. Okay, what do we know for this kind of formulation? Unfortunately, not too much. I mean, obviously, if you restrict yourself to piecewise constant functions to model the data term and the smoothness term, then basically you are back to the discrete label space setting, and then these results apply. If everything is convex in the first place, at least it's good to know that via this construction, which is making things more complicated and also relax certain things, that at least you do not change, or your relaxation is still tight in case you feed in convex functions in the first place. And for example, this does not hold as shown by some example for this kind of discretized Manford-Char-like functional. There is the common recurring theme for sufficient conditions when this kind of relaxations are tight is that the pairwise interactions are convex. So one would definitely assume that this is some ingredient here as well, but I don't know yet. So if it's the general setting, so the pairwise terms are convex, but the unit terms are only piecewise convex, then you can numerically construct counterexamples where the relaxation is not tight. So the question remains: are there some interesting conditions apart from everything being convex that you still get a tight relaxation? But this is an open and not yet solved problem. Okay, now very quickly to something completely different. So another problem. So this addresses much more the first problem for doing 3D correlation, that is getting to the point where you have these sparse point clouds and knowing the camera positions. So this involves a lot of robust estimation, robust fitting problems. And just at the bottom, so one simple example what robust fitting means. You have a set of points in 2D, and you know, or you assume these 2D points should be explained by a line, so they should lie on a line, but they might have noise because of the observation process. But also what you are assuming is there is a certain amount of outliers that are not on the line. So this calls then really to fit the line using robust cost functions, as indicated by this, I think Andrew likes to call it like psi-shaped robust cost. So meaning basically whatever is close enough to your model, so has small enough residual, you penalize it, let's say in some quadratic sense, in order to have like the nice properties of averaging, and but all residuals that are too large, they should not influence your answer. So this is also a very standard practice in correlation, but it also means using this kind of cost function. If you have multiple data points, you introduce many local minima. So for one data point, the robust cost here is like a quasi-convex function, so not too difficult to optimize. But if you look at some of these quasi-convex functions, they in general are very horrible to optimize. Okay, I guess this is just what I more or less tried to explain. We don't need to. So one kind of working horse in 3D computer vision is really like nonlinear least squares method, because it's fast, it's simple, and it does well. So, and there is kind of robust software out there solving these problems, and we might talk about problems that are relatively large scale. So there's a kind of a strong desire to recast whatever problem you have, as long as it's kind of continuous enough to recast it as a nonlinear least squares problem, just in order to be able to apply efficient solvers. So now the question is, nonlinear squares is very nice if you have the assumption of everything are inlier, so you have no strong outliers in your data. So then a least squares cost is a good choice. But in the case you're expecting outliers, and in correlation you do, or you have to. So what's a good way to integrate robustness into a nonlinear least squares solver? And standard ways in the past that have been used and proposed is, so one very standard way is called IRLS, so iteratively reweighted least squares, which is comes from like M estimators and so on. Is really just the standard method of choice. A bit more recent and elaborate method is recently termed tricks correction by one of the major software packages that people use these days. Basically, it's kind of a sort of a second order approximation of your robust cost in a certain way, but because this second order approximation might be non-convex, so it doesn't fit your nonlinear least squares structure, so in case it's non-convex, you do something about it, so you somehow convexify it. And a very interesting approach is what we call square rooting the robust kernel. Is you rewrite the robust kernel artificially as a least squares problem. So like in a way shown here. So basically you take the normalized residuals times the square root of your robust cost, which is non-negative anyway, so you can do it. You square it, you get back your original robust cost. So that's a way to address it as well. Are there other ways? Yes, there is. So one that is actually relatively old, so goes back to, I think, Giemann and Reynolds are the first ones of using it. Some others were picking it up and using it in different contexts. Basically, you rewrite your quasi-convex cost function as pointwise minimum over a set of parabola. And when you change the width basically of the parabola, the offset, so the height of the parabola has to go up. So that's this function kappa squared of w squared. So w squared defines the width of the parabola, and the kappa squared defines you in which way you raise the parabola basically. And if you look at the pointwise minimum of these parabolas, then you get back your original cost you started. So there are certain constraints when you can do these construction, but for our cost of interest, you always can do it. So what does it buy you? Actually, how it was used in the beginning, it was mainly used to accelerate computation in when you have this nonlinear robust cost terms, because you can separate. So once you fix W, so the width of the parabola, you end up with a standard least squares problem, and optimizing the W is a problem that's per observation or per residual, so it can be also done in closed form. So how it was used in practice, and that was called half-quadratic optimization, is really by alternating between updates of your unknown parameters and updates of your this confidence rates, or the width of the parabola. And what it also means, a byproduct, what it means is, so when you look at a robust cost as on the left, you see, unless you are kind of in this what we call inlier region, so near the zero, you have vanishing gradients, and this is always causing you problems. If you look at the kind of the joint residual and confidence rate space, or how this function looks like, you have, let's say, very few vanishing gradients. So you have the vanishing gradient at zero, but for zero residual, and you have a vanishing gradient for zero confidence. But everywhere else you have some gradients, which motivates to choose or to jointly optimize over your unknown fitting parameters that define the residual and this confidence rate, because you, in almost all cases, at least you have some interesting gradient. And this is how it is. So essentially, at the end of the day, you can rewrite, using this lifted formulation, your robust cost as a pure and not so difficult least squares, nonlinear least squares problem, and you optimize it jointly over everything. And because this confidence rate is really per residual, it doesn't hurt in your sparsity structure of the involved Jacobians and approximate Hessians. So it is up to some, let's say, small constants, equally efficient than not adding robustness at all. And the main application in 3D computation for this is what we call bundle adjustment. And so in the second part, I will kind of outline a bit what's happening. But essentially, you have to do a lot of tricks to get to some what we call initial 3D reconstruction, so that is roughly corresponding to the observed scene, but it is not fine-tuned yet. So you are kind of close to the solution, but it doesn't explain your image observations as good as it could, according to your noise assumptions. So what you do is you apply this kind of nonlinear least square solver onto relatively large programs that take as input, so like initial estimates of your cameras and 3D points, and optimize a robust cost over this and refine the structure in order to give you the nicest answers possible. And just some statistics, so that it's not exactly super large scale, but also not toy. And using basically this kind of lifting and joint optimization approach to optimize a robust cost function, generates, or the bottom line messages, gives you better local minima. You explain more data well, and it is not coming at a massive increase of computational cost. Okay, I think so. This construction can be a bit generalized. I think I'm skipping that part for the interest of time. And so now I come to the second part. So generally, the message is always you make the problem structure richer in your unknowns. That should always help. Like for random field inference, so you lift it to a high dimensional space, or for robust cost functions and many other situations. And I had a colleague in machine learning, and he said basically using more variables should always help, because you have more descent directions or more options to reduce your cost. But there's one particular instance of problem in geometric computer vision where exactly the opposite was the case, and this was puzzling us for quite a number of years, and we got at least some reasonable understanding what's happening there. So again, back to the motivation. So now we have images and try to come up with a reconstruction like this. So this is in general the problem setting, and as I said, in order to get there, that is kind of a delicate process. So basically you start with trying to find matches between image pairs, or all image pairs that are potentially seeing the same object or have something in common, and then you do some kind of local geometric verification, because these matches have to satisfy certain constraints if the scene is not deforming. So all the changes is your camera position, which is the case for like houses and so on, buildings. So you can do this is quite well understood and done. So then you have these pairwise matches. You kind of collect all the pairwise matches along the track to associate that with a 3D point with unknown position, but you are hypothesizing these tracks correspond to one 3D point that is projecting of unknown position, that is projecting into the image at the measured locations. So this is also reasonably well understood. But then there comes the magic. So taking this input to get you something that's close enough to the final output, the final 3D reconstruction. So there is a lot of various methods that are applied and proposed in the literature. Just to list a few of them, and this is, let's say, very ad hoc, not to say hacky. And the only final thing that's also very well understood and like a gold standard is run like this band adjustment with nonlinear least square solvers, usually with some robustness at the end. So, but the part in the middle is a bit tricky. So one of the questions is, why is structure for motion so difficult? So and especially, why can't you just initialize things randomly and let the optimizer find out a good solution, which is almost never working. clearly one of the troublesome components is, even if you do matching and do some sort of verification, you still have a certain amount of what we call outliers, so mismatches or false positive correspondences, and especially in man-made environments where one corner of a window looks similar enough to another corner of a window but unrelated window. So that is happening quite often in repetitive environments, and they like to be in man-made environments. That's clearly one of the problems, but even if we take out this issue of robustness, how difficult is this the non-robust band adjustment cost function? And in this, I didn't write down the band adjustment cost function, but what it involves is some certain bilinear term. So you have camera matrices denoted by P or Pi, and you have 3D points denoted by Xj. And in order to find out what is the image projection, you have to multiply these two matrix times vector, both are unknown, and then you apply a nonlinear operation, this pi, which is a projection, onto the image. And usually you're interested in what we call metric band adjustment. So this matrix Pi has a certain structure. That's also one of the complicating facts. But there are some examples when band adjustment seems to be like an easy problem with a large basin of convergence, where you can start basically from some random initial points. And one of the examples is if you have extremely small motion, and there's some paper recently that is called like structure for motion from accidental motion, and sometimes you can verify that a local minimum that's found can be, or is verified as being also a global minimum. I think Carl worked on this as well. We start from some different setting. So we restricted ourselves to what we call a fine structure for motion by taking out first this nonlinear image projection, and there it turns out that in the past what's called the V-Berg or Weiberg algorithm is doing extremely well, even starting from random initial values. So, and just trying to give some intuition about this. So the fine structure motion, because there is no, so the camera model is quite simplified, so you don't have the pinhole model, and you don't have this perspective projection in there. So the image observation is just explained as basically the matrix product, camera matrix times the 3D point, and you have given measurements in the image, and you want to find camera matrices and 3D points that explain as good as possible your observations. And I think Carl also briefly explained this problem. So if you have everything observed, so every 3D point is observed in every image, then this is easy to solve via SVD. But in almost all interesting cases, you have lots of missing data. So a 3D point is only observed in a relatively small subset of the images, and this is exactly what makes this matrix factorization problem extremely hard. So the like naive way to solve this problem is okay, minimize just over your camera matrices and your 3D points this cost function. This almost never works, and it's reported a number of times in the literature that this method fails. And eventually, so over time, there was kind of gradually some conclusion that what really works very well is what we call the V-Berg method or variable projection method in other literature. So essentially what you do is you optimize over the 3D points, in this case in closed form, and plug in the more nonlinear expression into your original cost function, and then apply your favorite nonlinear least square solver on this reduced problem. So you, instead of lifting, you do kind of exactly the opposite. You make the problem less rich in terms of the unknowns, and also harder in terms of how your cost function looks like, because instead of a like matrix factorization problem, you are looking at a much more nonlinear problem instance. And just to illustrate what kind of this means, we have our favorite dinosaur picture, although is it dinosaur or Godzilla? I think for some reason it's always called dinosaur. So, and kind of here is depicted the observed tracks, and when you do the structure of motion computation, what it allows you to do is kind of to predict where the 3D points would be projected in the other images. And so the sequence is a turntable sequence, so the fact that every track is an image on a circle, so it tells you, okay, this is a nice reconstruction. Okay, and so for example, for this particular problem instance, what you get if you do this joint optimization over all the parameters from random starting points, so random according to some drawn from a standard Gaussian distribution, you get basically 0 or few percent convergence to what is assumed to be the best solution you can get. And if you run the Weber algorithm, you observe like 90 to 100% success rate from starting from the same kind of random initial data. So what is going on? So we thought for a long time that for some magic reason, because the different formulations or different the formulations to optimize take different paths, so you would end up for some magic reason in just a much worse local optimum when you do joint optimization, and for some magic reason the variable projection or Weber algorithm gets around this optima. So this is what we often believe, but turns out this is not the case. Also not the case that this Weber algorithm is good on all problems. So for certain problems in machine learning, where you also have this matrix factorization structure, is not doing that great. So there are still unanswered questions why Weber does so well, but at least the thing we can answer now is why joint optimization doesn't work well. So our belief was always it reaches a different local minimum that is for some reason not very good, and after lots of investigations and wrong hypotheses, actually we realized that the optimizer doesn't reach a local minimum, it actually stalls. So it stops making progress. And one might ask, is this specific to like the Gauss-Newton approximation? And in the literature it was reported by, and if it's given that damped Newton performs equally bad. So that's common to a number of optimization methods. Maybe I can try to show if I manage some video. Just to give you an idea how these optimizers behave and how they find the solutions. So you started from random initial configuration, so everything was messed up. So this is the Weber algorithm / variable projection method. This is joint optimization, which just gets stuck somewhere and you don't see a sensible 3D structure. Okay. Let's do and after some time, what John, one of the students I and Andrew work with, what he realized is that actually, so joint optimization and VARPRO, or let's put it that way, VARPRO is extremely closely connected to what's called the Schur complement in the literature. Basically, so when you do joint optimization, what the message here is, what you have is something like a regularized Schur complement. So this lambda is kind of a damping parameter that is applied in joint generalization on both the camera matrices and the 3D point structure. Whereas in the VAPRO method, essentially you use a Schur complement, but only with damping on the camera matrices, but not on the 3D points. And this, at the end of the day, makes all the difference. And after some time, I think I kind of have some. I mean, also by identifying Schur complement and VAPRO as basically the same, one of the byproducts is you can implement VAPRO much more easily. So in the past, people derived manually the kind of the gradients. You don't need to do it. You just use at the end of the Schur complement. So you get kind of efficient. If you have an efficient, let's say, Gauss-Newton solver using a Schur complement inside, which is the case for all the convolution implementations, then it's very easy to upgrade this solver to incorporate VAPRO approaches. But in terms of what is happening, so why did this joint optimization is dark, I try to, not too well, but still try to illustrate what is happening, at least in this 3D convolution setting. So imagine you have your set of cameras, and by random chance, two cameras are almost parallel, so looking almost parallel. So which means the underlying 3D points would be triangulate kind of at a distance, at a large distance. And now if the camera's parameters want just to change minimally, this also just implies that your 3D points have to change massively because of the poor intersection angle. But this 3D point changing a lot is prevented by this Levenberg-Marquardt damping factor because you regularize the updates of the 3D points. So in this exactly yields to this behavior that the optimizer stops making progress because for the camera parameters you want to somehow update them, but basically the points being very far the distance are just preventing from the update to happen, and so that's why it gets stuck. Okay, we had this video, and basically one of the things we're suggesting is a revised or simplified structure for motion pipeline. So the first three steps basically are the same as understood in the literature. For the fourth one, it's either this magic. We are saying, okay, we just run variable projection because it's so successful, either on like a fine camera model, or we have something here. It's the working title, semi-projective. We call it slightly different now. So that gives you, from random starting point, a good initial solution right away, and then you refine everything potentially robustly using the regular matrix boundary adjustment, because you have a solution that's generally close enough to be in the convergence basin for the nonlinear optimizer. Just a small inset illustrating so difference between a fine and this semi-projective reconstruction. So on the top, this is kind of the ground truth configuration, and the point cloud and the camera are seen as from a bird's eye view. On the left, you see kind of the initial affine reconstruction, and then our kind of revised cost function, which still has the properties of being like matrix factorization-like, but it's just better modeling. The pinhole camera model gives you something nicer. I can skip this. Maybe I should, at this point, show the second video, which might be hopefully yes. So random point clouds, no structure. So you optimize this bilinear problem. You get already some good structure, so this projective refinement is not doing too much. And then at the final stage, you do kind of a what we call matrix self-calibration step to get to a nice model that lives in metric space. Here another example, I think that's data captured by Carl. And I think the final example, which is quite difficult for the approach because it has lots of what we call depth variation. You will see in a second. So this is one of the examples where kind of the surrogate cost function we're using that has a large Bayesian of convergence is not exactly modeling the pinhole camera model. So because you have this large difference in depth range, so some of the 3 points are very close, some of them are very far. So the result of this first stage, so of the bar probe method, is still not as close. So it's still refined by the later stages that are conforming to this the more realistic pinhole camera model much better. Okay. So here, so just some pictures of some further examples. And basically, in summary, I would say if you can do lifting, it should always help. There are some cases, and I've shown two, where kind of interference with the optimizer might lead to suboptimal results. So if you do alternation, be careful that it could lead to like too early commitment of certain variables, and you cannot escape certain bad solutions. So there's one pitfall, and with second order methods that usually require, or second order trust region methods, so there might be some, let's say, surprising interactions between the trust region parameter and your program structure, such that it prevents you from updating in the right direction. That's it. Thank you.
Structure from motion solved.
Good question. At the end, I don't think so. For, I would say, two reasons. One is just more like practical, and one is more fundamental. So there's still lots of parameters going in, and also doing things very large scale. Basically, you break it down into like smaller chunks that are easier to manage, and then you stitch everything together. So still there are a number of parameters and tweaks and so on to do. So this is the kind of the practical thing. It's not always working off the shelf. The second, the more fundamental answer is no, because nothing addresses really difficult scenarios. So try to reconstruct a skyscraper with lots of glass facade. Then it's and there, I mean, all the assumptions just break down. So I would say it is solved to a large extent, that you can give software to end users, and in certain settings you will get a good result. But I wouldn't say structure of motion is solved in general.
Any other comments?
Could you go back to this stalling case?
The what case?
The case where it stalls, you know, you have the almost parallel race. Actually, you don't need to go back, but isn't this a case where you have? Could it be a problem with the parameterization, because you will take a large step in your parameters, but the matrix is not going to change much?
Yes, and the thing is, you can force joint optimization to work if you massively rescale the initial values, such that, let's say, the 3 points are divided by 1 million. The camera radiuses are multiplied by 1 million because you have the scale shooting in between. Then the success rates go up. So in a way, it's confirming our intuition on what is happening there. So but the point is, we start with you would start with balanced kind of initial values, and then it seems like the optimizer just drives the points to very large values, with not changing the camera matrices too much, and then you end up there. So strategies as like somehow rebalancing the variables on the way could be helpful. I think John started looking into this a bit, but not too much.
In the earlier part, you mentioned something called tight approximation or
Tight relaxation, yes.
or something. What's the meaning?
Oh, it is. So if you have an original problem and you have a convexification of the problem, so the question is the convexification really strictly giving strictly smaller optimal values than in your original problem?
Tight means they have the same.
Tight means they have, so solving the relaxed problem is equivalent to solving the original problem.
Thank you.
Speaker again.